by this union. And if we see, like it is over n is equals to 0, 1, 2 and so on till 0, 1, 2 and so on till infinity of all like finite decimal like numbers of the form summation I is equals to 0 to n 10 to the power of ai, and ai is belong to 1 to 2. So that means for a fixed n, if we fix a particular value of n, we are having 2 to the power n plus 1 such numbers. So this is nothing but a finite thing. So that means this whole set is countable union of finite sets. So that means it is countable, but in the question they have given it is uncountable. So therefore option A is wrong. If we consider the second statement on the other hand, so we are having like a1, a2 and so on till an, with an belongs to this 1 comma 2. I mean like a1, a2 and so on. So that means we can clearly see like if x belongs to, x is n is equals to 1 to infinity, an by 10 to the power of n. So the set is in bijection with the set like 1 comma 2 of infinite 1 comma 2 sequences. So a set of all infinite binary type sequences is uncountable by Cantor's diagonal argument. So if we consider the set of real numbers here, so that is uncountable. So therefore like option B is correct. Now if we see the option C says there exists an uncountable set whose elements are pairwise disjoint open intervals in R. And option D says the set of all intervals with rational endpoints is uncountable. So if we consider the third statement, suppose if we consider like, suppose I is a family of pairwise disjoint open intervals in R. So that means each interval contains at least one rational number. And we know like two distinct intervals contains like two distinct rationals because the intervals are disjoint here. So that means like we are getting an injection here from this I, which is a family of pairwise disjoint open intervals, to this set Q, and this rational number Q is countable. So that means I must be at most countable. So therefore there cannot exist like uncountable. There cannot exist uncountable family of this pairwise disjoint open intervals. Therefore C is false. Now if we consider the fourth statement, so an interval with rational endpoints is determined by this pair, let's say P comma Q, where this both belongs to Q and Q, such that P is less than Q, let's say. So Q cross Q is countable because it's product of two countable sets. So the set of such intervals is countable, not uncountable. Therefore option D is also false. So option B is the correct answer.